There we go. All right, welcome. You should know by now that the exam 2 has been posted on Canvas. That was emailed out earlier, that it's there, but it is there. So if you haven't started on it, go get it and start on it. It'll be due next Monday, which is the, what is that, Halloween? Yeah, so on the 31st. So, and that'll be in class. So make sure you're there, bring it in, and all right, here we go. Let's start in on chapter 5. So 5.1 is inverse functions. So we would start by talking about what an inverse relation is. And remember that a relation could be something as simple as just a set of x and y coordinates. So something like 2, 3, 4, 8, right? 9. There doesn't have to be any rhyme or reason in it. This is a relation, right? It happens to also be a function, simply because for each individual input, such as 2, 4, or 9, each one of those goes to only one output, right? And that's what makes it a function as well. Okay. We might have others, right? We might have, say, 2, 7, 2, 9, 8, 4. And it doesn't matter. There could be a million points in this thing, or there could be a very small number of them. But this is also a relation. This one is not a function. And it's not a function because the input of 2 goes to 2 different outputs, right? In one instance, it goes to 7. In the other instance, it goes to 9. And so that makes this thing not a function, right? And so an inverse relation let's do this I'm going to do this relation up here. If I just take all of my points and switch them, so instead of 2, 3, I'm going to have 3, 2. Instead of 4, 8, I'm going to have 8, 4. And instead of 9, 10, I'm going to put in 10, 9. Then this is the inverse relation of, so this right here is the inverse relation of the original relation that we had in red. Likewise, if I want to do the inverse relation of the blue one, then I can have, instead of 2, 7, I have 7, 2. Instead of 2, 9, I'll have 9, 2. Instead of 8, 4, 4, 8. Instead of 37, 42, I have 42, 37. Okay. And so this one here, this is a function because each of my inputs goes to an individual output. So 3 only goes to one place, it goes to 2. 8 goes to 4, 10 goes to 9, right? So this is a function. And this other one is a function, but it doesn't matter, right? So this is a function. But it doesn't really matter because it's the inverse of something that wasn't a function, right? So it's great that it's a function, but since the first thing wasn't a function, we wouldn't talk about it in the same way we would talk about a function. But this guy here that we've created for the red one, since this is a function of simply having inverted a function, that makes this the inverse function. And so we would call this the inverse function. That's what this is. It is the inverse function of the previous function. Okay. So that's essentially what it is. In short term, like we'll have things like f of x is a function, right? These previous ones that we were just dealing with were discrete functions, meaning there's just a finite number of points in them. But f of x equals, let's say, x squared is a function. And we would say that its inverse function, which is denoted with an f with a little -1 as a superscript, right? A lot of people like to think of it as a power. It's kind of not, right? But it's using the same kind of notation. But f inverse of x is how you would read that in orange or yellow or gold or whatever this is. But the inverse function of this is to take the square root, right? The inverse function is the function that kind of undoes the original function, right? Or we could simply say that this way, the inverse function also can be said to swap the x and y values. Right. So for example, in this function, x squared, if I say f of, let's say, 2 is 2 squared, which is 4, right? F inverse of 4 is the square root of 4, which is 2. And so all I've really done is created a function that swaps those two every single time, right? If I try something else, f of 7 is 49. Well, that should mean that the f inverse of 49, right, taking the f inverse of the y value of my other function should give me the x value of my other function. And it indeed does. And so that's the idea behind an inverse function. Now, when we start taking inverses, I can see things such as, let's use that function we just did, f of x equals x squared. Right? Now, obviously, if I graph this thing out, it becomes quite clear. Right? That's my graph. If I just take a few samples, like here's a point here, there's a point 0, 0. If I took a point here and let's say that that's at 1, I know that my y value is also going to be at 1, so I have the point 1, 1. And then I have at -1, also 1, right? And this is still a function because the value of x being 1 only goes to one place, being 1. The value of -1 only goes to one place. It just happens to be the same as the output for 1. But I can do this a lot of times. I can say, well, if I evaluate this thing at, say, 2, x squared is 4. But if I evaluate it at -2, it's also at 4. So this thing is still a function. That's not under question here. What we're worried about, though, is when I try to take the inverse, right? If I just focus on these points right here and don't worry about anything else, right? The inverse of these points would give me well, 0, 0 turns into 0, 0. 2, 4 turns into 4, 2. -2, 4 turns into 4, -2. And then I've got, let me just scooch this up out of the corner here. I'd have points like, say, 1, 1 and 1, -1, right? And what I can say about just the points that I've created, right? I'm just looking at a few points on this graph. The inverse function, or the inverse of the function, does not appear to be a function. Because I have points like 1 that goes to 1, and then 1 that goes to -1, right? Likewise, 4 goes to 2, but also 4 goes to -2. That's what makes this not a function. And we could have foreseen that by up here seeing that an input of 1 goes to 1, but an inverse of -1 also goes to 1. That's fine to still call this a function, but then this is not what we would call a one-to-one function. And so a one-to-one function has for every spelled with for every input, there is one, or let's just say a unique output, right? Which means in this case, this is not a unique output. 4 goes to 2, but also, oh, my bad. Look at the back one. 1 goes to 1, right? Like we said here, but also -1 goes to 1 as well. So this is not unique. And we need it to be unique in order to get a one-to-one function. And the reason that we care about that is that the inverse of a one-to-one, sometimes you'll see it spelled out as 1, 2, 1, or just 1-1. But the inverse of a one-to-one function is a function, right? But the inverse of a function that is not one-to-one will still be a relation, but it's not going to be a function, right? And so we would, and I did this, but didn't make any mention of it. Back here I said, oh, there goes my 7. Back here I said, this relationship exists. If your function is x squared, then your inverse function is the square root of x. But that doesn't really work for every x. For example, if I take f of x equals x squared, and I try to evaluate f of -2, I got 4. But there's no way of plugging in this 4 into my other inverse function and getting -2 back out of it. Because this is the principal square root. It's the positive square root of x. And so what I've done here is limited my domain. Because this root of x has a natural domain of x has to be greater than or equal to 0. Right? That just comes with that square root function. So what I've really done is only taken one of the little bits of the parabola and said, well, we're just going to work on this part of it. And so in order to make that work, what we typically do then is restrict our domain. So for example, if f of x is equal to x squared, again, I graph this thing and I get that parabola. But then if I say, well, I'm really only interested in this part of it on the right-hand side, this part right here, I can just ignore the other part. I can just say, well, let's just pretend you're not here for a minute. And if I do that, now it's a one-to-one. So if I say f of x is equal to x squared, and I come in and say 4x being greater than or equal to 0, now I have a one-to-one function, right? I've basically kind of chopped off the left end of this parabola and said, I don't really need you here. And so this bit right here, along with that domain restriction, is now one-to-one. And so I can come in and say, then my inverse of this thing, f inverse of x, is square root of x. The implied domain here, though, is that x is greater than or equal to 1. We don't actually have to write it out because it's obviously implied. And therefore, these two are now inverses. This inverse function is valid for that domain restricted function. To show that two functions, let's back up. To show that a function is one-to-one, right? What we're going to do is we're going to evaluate the function at 2 points. There are going to be two unknown valued points. So we'll say at just A and then at B. And then if you can show that A has to be equal to B, then it's one-to-one, right? So what does that mean? Well, let's take a look at an example of this. So we want to prove, and they'll ask, a lot of times they'll ask you either to show or prove, but we're going to prove that f of x being 2x minus 3 is one-to-one. Right? So I'm going to do this. I'm going to say, well, I'm going to evaluate this at 2 points. I'm going to take f of a. Again, they're just two random unknown points. You can't just say, well, let's do it at 1 and 2 or 3 or 4 or whatnot, because there are some where it just happens to be the same at those 2 points. You have to show it everywhere. So f of a is 2a minus 3. And f of b is 2b minus 3. Right? And so the point is that I want to show if f of a is equal to f of b, right? This is our assumption. We're going to assume that f of a is equal to f of b. Then the only conclusion is that a has to be the same thing as b, right? So we start here. We assume f of a is equal to f of b, and so I set f of a, which is 2a minus 3, equal to f of b, which is 2b minus 3. So we make that assumption. So we assume that 2a minus 3, right, which is the function evaluated somewhere, I don't know where, just wherever that happens to be, is equal to 2b minus 3, which again is that equation evaluated anywhere. Pick a b, it doesn't matter. But if I can prove, and it should be obvious that it's true here, if I can prove that a has to be equal to b, then of course, then this thing is one-to-one. And so I'll add 3 to both sides using the addition principle of equations. And that gives me 2a has to be then equal to 2b. And then, of course, if I divide each side by 2, I get a equals b. And so that's the whole point, is you evaluated at a, evaluated at b, assume that the function evaluated at a is equal to the function evaluated at b, and then mathematically show that it is a requirement that a equals b as a result of that. Okay. Let's take a look at another example of that. Let's do 1 over x, right? So that f of x equals 1 over x is one-to-one. And so I'll take f of a to be 1 over a. And that's it. It's just 1 over a. And then f of b is just 1 over b. And again, I then just assume that f of a, which is 1 over a, is equal to f of b, which is just 1 over b, right? And I have all these things. So this is valid for as long as the domain of the original function is that x can't be equal to 0 anyway. And so it is assumed that A isn't 0 and that B isn't 0. Otherwise, we're not working within the confines of this function anyway. And so I can multiply both sides by A and B. The A cancels out on the left, leaving me with just a B. The B cancels out on the right, leaving me with just an A. And I've got it down to, in order for the function evaluated at one place to be equal to the function evaluated at some other place, the only way that happens is if that place is the same place, B equals A. One that doesn't work out is the x squared that we just talked about. X squared is not 1-to-1. It's obviously not 1-to-1. The graph of it looks like this. So that's not sort of, well, that's sort of what it looks like. Zoop. And so I can see, well, there's a place where I get a y value, and there's a place I get the same y value, right? I know it's not 1-to-1. Mathematically, algebraically, how do we show that? Well, again, I just say f of a is equal to x squared, and f of b is equal to b squared. And so I assume, oh, my bad, not x squared, but a squared, right? Then I say, all right, well, let's let a squared equal b squared. But is this true? Then does this mean that a has to be equal to b? The answer is no, because of the square root principle. If a squared equals b squared, but then by the square root principle, a is either equal to the positive or the negative square root of b squared, which is to say that a is either equal to b or a is equal to negative b. Right? And so because it comes down to this conundrum, it's no longer a function. It's no longer a one-to-one function. And therefore, because I know it's not a one-to-one function, I know that its inverse is not going to be one-to-one either. Or I'm sorry, its inverse is not going to be an actual function, is what I know from that. All right. As indicated right there, right here, there's a way that we can tell if we're looking at the graph of something. I'm going to just grab this picture here real quick, plop it right there. There's a way to tell if we're looking at a one-to-one function if we're looking at the graph, and that is the horizontal line test. And the horizontal line test essentially is if you can put a horizontal line anywhere through the graph and hit it more than one time, then it's not one-to-one. So I can throw a line through this is a parabola. I can throw the line through it anywhere and hit 2 points. It's not one-to-one. Likewise, this function here, 3x to the 5th minus 20x to the 3rd. Well, there's a line right there that hits it 3 times, right? There's a line here that hits it 3 times. There's a line here that hits it twice. There's a line here that hits it twice. If at all, if it fails anywhere, then it's not a function, right? I'm sorry, it's not one-to-one. All right, so here, this cube root of x plus 2 plus 3, I can't throw a line anywhere and hit this twice, right? It's hard enough for me to draw a straight line, but I can't draw a line that's going to hit this twice anywhere. So this is one-to-one. Likewise, 4 minus x, this, any line that comes through this is going to hit that function just once. And so this is one-to-one as well. Okay, and I'm going to steal this picture right here. So this is how we're going to go through and find the formula for an inverse. I just didn't want to write this, so here it is. But if I have a function, for example, and it says find the inverse of, let's say, let's that 2x minus 3, f of x, 2x minus 3. Okay, the first thing I want to do is replace f of x with y. So instead of f of x right here, I'm going to call that y. Just to get out of the functional notation, y equals 2x minus 3. And then the next thing, I'm going to interchange x and y, right? So instead of y equals 2x minus 3, I'm now going to call this x equals 2y minus 3. So what I've done is now just rename these things. X is now y and y is now x, but that y now that I have written here is my inverse. And then I'm going to solve this thing. The last thing, not the last thing, the biggest thing is to solve for y. So this y right here, I want to solve that equation for it. So here, it's pretty easy on this one. I just add 3 to both sides. That becomes x plus 3 equals 2y. And I divide each side by 2. So I've got y equals x plus 3 over 2. And then I'm going to rewrite it. I'll just rewrite it over here. Y equals x plus 3 over 2 with the y on the left-hand side. The very last thing I'm going to do is replace that y with f inverse of x, because that's now what this function is now it's the inverse function of x. That's x plus 3 over 2. We'll do the same for this equation. F of x, let's say, is x to the third. Oops. The third plus 7. Right. So again, the first thing that I'll do here is f of x. I'm going to rename this. Just we'll replace it with y. And then swap them. So instead of y equals, I'm going to have x equals y to the third plus 7. And then solve for y, right? This third step, solve for y, is typically the one that takes the most energy, the most work. But let's do it. It's not terrible here. Let's subtract 7 from both sides. That gives me x minus 7 equals y to the third. And then I just need to take the cube root. So that would be the cube root of x minus 7 equals y. And then I'll replace that y with f inverse. And so in the end, I have, and I'll write it on the left, right? So this y becomes f inverse of x. And that function is just the cube root of x minus 7. And that's it. I'm done. They can get a little bit hairy. Especially, let me do one that is about as hairy as you'll expect it to be. See if I can find there. There we go. All right, so this is about as ugly as these are going to get for you guys. Let's say we have f of x equals x plus 4 over x minus 3. Because any more ugly than this, and you're talking about just throwing it into a computer and saying, screw this, I don't want to do this. But for now, right, we'll just go through the same process. I'm going to rewrite f of x as y. And you can, of course, as you do these, you can do this all a little bit more quicker. You can just say x equals y plus 4 over y minus 3. You don't have to do every step every time, right? But then I would switch. So this becomes x equals y plus 4 over x minus 3. Oh, sorry, not x. Switch all the y's and all of the x's, so y minus 3. And now what makes this hairy is that you've got two y's and you need to solve for y, right? But what I'll do is clear this fraction by multiplying the right and the left-hand side by that denominator term of y minus 3. Because the y minus 3 just cancels on the left-hand side. But it becomes x times y minus 3. I'm just going to distribute this. I'm going to write this as xy minus 3x equals, on the right hand side, then I have just y plus 4. So from here, what I'll do is I want to get all of my y terms onto one side, so I'm going to subtract y from both sides. But I want this 3x out of my way, so I'm going to add it to both sides. And I'll clean it up a little bit. So here the 3x cancels off the left on the left-hand side, and I'm left with xy minus y. And on the right-hand side, the y cancels out, but I'm left with 4 plus 3x, or 3x plus 4, if we like. And the reason I want all of my y's on the left-hand side and nothing else is because I can factor out a y. And now all I have to do is divide each side by that term of x minus 1. So the x minus 1 term cancels with the x minus 1 term there, leaving me with just a y on the left-hand side, and then this fraction, 3x plus 4 over x minus 1 on the right, and I'm done. And that's about as ugly of a problem as you'll see. And then the last little bit in this section is to verify two functions. There we go. All right. That is in short. Oh, all right. Cool. That. So to verify the two functions are inverses of each other, their composition should equal x. So that is to say, if I take f composed of g of x, that should be the same thing as taking g composed of f of x, which isn't always the case. But if they are equal, and specifically they both equal x, then g and f are inverses. So that is to say, if that, then f, let's say this, g inverse of x is f of x. And likewise, f inverse of x is g of x. They're inverses of each other. Right? So to test that, we just compose. So we would say if f of x equals x minus 8 over 5, and g of x equals 5x plus 8, Then we would show that they're inverses by taking f composed of g of x. So that's plugging g into f. So that is 5x plus 8 in place of the x, and then minus 8, and then over 5. But we can simplify because 8 and minus 8 cancel out. So this is the same as having just the 5x over 5. But 5 over 5 is 1, so I end up with x. Likewise, I should be able to take g composed of f, and it should also simplify down to x. And so let's try that. I'm going to take 5 times, instead of x, I'm going to plug in f, so x minus 8 over 5, and then plus 8. But the 5's cancel here. That leaves me with x minus 8 plus 8. But minus 8 plus 8 is 0, x plus 0 is x, and I'm done. So you just have to typically do it once. F of g should equal x. If f of g equals x, then g of f should also equal x. If it doesn't, something super funky is happening, and most likely it's algebra mistake somewhere. But yeah, so typically just do it once. Okay. All right. All right, we've got to move on. Any questions on that? Okay. Then 5.2 is exponential functions. So an exponential function looks like this. There'll be some number as a base, but x in the power, right? So for example, we might have f of x is 2 to the x, or f of x equals 5 to the x, or f of x equals 0.003 to the x, right? It's just going to have some base power, right? So in this case, 2, 5, and 0.003 are called the base. And then the x is the exponent, which is why it's an exponential function, is because the exponent is the variable. We would note here that we're not talking about things like f of x equals x squared. That's not exponential. X is the base. The 2, the exponent is fixed, right? We're not talking about, anything like this. 1/2 to the third. That's just a number. That's not even a function of x, right? We're not talking about having some, expression raised to a fixed power, right? We're not talking about 3x minus 2 raised to the 5th power. These are not exponential because the exponent is not variable. Okay. So we can evaluate a couple of points. Let's graph. Let's do 2 to the x. And we'll do that by evaluating some of the points. We'll graph some x values, we'll graph some y values, and then we'll graph this whole thing. But if I graph some, let's say 0 and 1 and 2 for x values, if x is 0, y is 2 to the 0, but 2 to the 0 is 1. Anything to the 0 power is 1. 2 to the 1 If x is 1, then y is 2 to the 1. That's just 2. If x is 2, that's 2 squared, which is 4. And so if I start to graph this now, I get, can I do a graph on here? That's not helpful. What is this? Oh, all right. If I graph these points, I've got 0, 1, right? So my x value is 0, my y value is 1, so that's a point, say, here. At 1, I'm at 2. And then at 2, I'm at 4. And it may not be very easy to see what's happening with this graph. So I may even want to go out more. I may even want to say, well, what happens when x is 3? If x is 3, then y is 2 to the third. But 2 to the third is 2 times 2 times 2. That is 8. So at 3, I'm all the way up here. At 8. And so it might be tempting to just come in here and say, well, it looks like it's a straight line, which I could not try. But it's not really great straight line, right? This point up here is way off. This point's down. So let's get a better look at what's happening by maybe taking some negative x values, like -1. But if x is -1, then y is 2 to the -1. But having a negative power means that I have that power of 2 in the denominator. So that's 1/2. And if I have, let's say, x is -2, then that's 2 to the -2. But again, that's like having 1 over 2 squared. Put it down in the denominator, but that's 1/4. I can keep going, but I think I've got a pretty clear picture here. If x is -1, then I have a point at 1/2. If x is -2, I have a point at like 1/4. And I can keep going, but it probably is a little bit more clear where this is headed. This is going up like this, and it's going to be increasing faster and faster as I go to the right, right? That's not a great line, and I'm going to copy and paste a better graph that is in the book here in a minute. But what about what happens to the left of this thing? What happens? Am I ever going to cross over and go into the negatives? Because it looks like it's just going down, down, down. And if I go down forever, I should hit negatives at some point, right? But we can take a look at this by just saying something blatantly hugely out there. What if I took x to be -1,000? Well, then I would still have 2 to the -1,000 for my y value. But again, that's just shoving that 2 to the 1,000 down in the denominator, but that's still a positive number, right? It's 1 divided by a lot, but when you divide by a very large number, that becomes not a lot. I don't know what it is. I don't really care, but it's not negative, right? And it doesn't matter how big this number gets in the negative, -1 million. I don't know how many zeros that is, but 1, 2, 3, too many. So that's -1 trillion. That's still going to be 2 to the -1 trillion. Lost count there again, but that's 2 to the 1 trillion. 1, 2, 3, 4, 5, 6, 7, 8, 9. Doesn't really matter. It's still positive. It's ridiculously small. And it's going to get smaller and smaller and smaller the more it goes out that direction, but it's still going to be positive. And so this thing will actually never get to 0. And so we would say it asymptotically approaches that line. And it's going to get closer and closer and closer, but will never touch. And so a lot of times you might see a dotted line here. Where's my dots? Right? That it asymptotically approaches the x-axis. And it never actually gets there. But this is the general idea of what a exponential function looks like. Let me still a better. It even has that explanation right there. How nice. There it is. Right. So this is what x 2 to the x looks like in a much better graphed line that doesn't look like Parkinson's disease drew it. But it's very smooth, but it gets, faster and faster as we go to the right. And then it gets, less and less of a slope as we go to the left, and it approaches that x-axis, but it's never actually going to get there. It's never actually going to touch it. Okay. Well, let's take a look at this one, 1/2 to the x. We'll go about it the same way. I'm going to get some x values and then figure out their y values. So if x is, let's do the same thing. Let's just go 0, 1, 2, and I'll grab -1 and -2 as well. But if x is 0, then y is 1/2 to the 0. But anything to the 0 is just 1. So you're going to see this a lot, that when x is 0, your output is 1 until we start shifting it. But if x is 1, then I get 1/2 raised to the 1 power. But anything to the 1 power is just itself. So that's 1/2. And then if y is, if x is 2, then y is 1/2 to the 2. But that's like 1 squared, which is 1, over 2 squared, which is 4. And then likewise, if I do x is -1, I get 1 over 2 to the -1, right? And so I'll do this off to the side here. How do I treat this? Well, 1 over 2 to the -1 is 1 to the -1 over 2 to the -1. And anything with a negative exponent, you're just going to swap places. So 1 to the -1 in the numerator becomes 1 to the +1 in the denominator. And 2 to the -1 in the denominator comes upstairs as a 2 to the +1. But this is just 2 over 1, and that's just 2. Likewise, 1 over 2 to the -2, through the same process, I'm going to end up with 1 to the 2 in the denominator, and 2 to the 2, which is 4, in the numerator. And anything over 1, I don't really care about the 1. And so if I graph this guy, all right, for crying out loud. Try to get at least some sort of order to this graph. I've got a point at 0, 1. So once again, I've got 0, 1 right there. I've got the point 1 and 1/2, so that would be half as much. The point 2 and 1/4. So I can see I'm kind of getting that asymptotic approach to the x-axis now on the right-hand side. Whereas if I go to the left-hand side, I've got -1 and a point at 2. And then -2 and a point at 4. Right? And so then I end up with this graph that looks like this. And then increases sharply to the left, right? So this is the graph of 1/2 raised to the x. And so in contrast, it looks like the graph, if I can find that graph. This looks like this graph, but it's just been rotated about the y-axis. That's all it looks like, right? And the reason that is because I can say that 1/2 to the x is the same thing as 2 to the -x. That's the same thing. And all that is flipping that thing about the y-axis. We can, of course, use some of the graphing strategies that we've talked about. If I want to graph, let's say, f of x equals 2 to the x plus 3, right? Well, if I start, I can go through and do x and y points, right? If I say x is 0, then y is 2 to the 0 plus 3. But 2 to the 0 is 1, so 1 plus 3 is 4. If x is 1, then I have 2 to the 1 plus 3, which is 2 plus 3, which is 5. If x is 2, I have 2 to the 2 plus 3, but that's 4 plus 3, and that is 7. Right? If I do negatives, let's go -1, then I have 2 to the -1 plus 3. 2 to the -1 we saw was 1/2 plus 3, so this is 3.5. And -2 is 2 to the -2 plus 3, but 2 to the -2 is 1/4. And so I get something like 3.25. And if I graph this out, someday I'll get a straight line. Not today. I've got some points. I've got 0, 4. So 1, 2, 3, 4. Let's say it's there. At 1, I'm at 5. At 2, I'm at 7. On the left-hand side here, at -1, I'm at 3.5. So here. And then at -2, I'm at 3.25. And I can see what's happening on this side is this. And on the left, this is just going to asymptotically approach that value 3, because what I've essentially done is just taken the graph of 2 to the x and then shifted it up by 3. And so if I want to take a look at something like, let's say g of x equals 2 to the x minus 4, I don't have to go through my x and y charts, right? All I know is that this is going to be 2 to the x, which I should have a general idea of what that looks like. And then I just shift it down by 4. And so without going through my XY charts, I should end up with something that looks like this. It's 2 to the x. Oops. Little bastard. There we go. And it's just been shifted down by 4. So everything, that asymptote included, moves down by 4. So instead of having an asymptote here on the x-axis, all of that is shifted down. And I have the asymptote down there at y equals -4. Right? And bam, it's just a drop, right? And so likewise, we can see a shift within the, the left and right. So we might see something like, say, h of x equals 2 to the x plus 1. And this is going to just be a shift to the left because that plus 1 is within the x, right? And so 2 to the x plus 1 is 2 to the x, but shifted to the left. So I'm going to have a point at -1, 1. And this thing just kind of is that 2 to the x, but shifted left by 1. All right, we've got time still. Okay, good. So one of the applications of these types of functions is compound interest. So if I have this function here, a is equal to p multiplied by 1 plus r over n all raised to the t. Okay. So the A is a function of time. It's the amount in the account. After T years. P is the principal. It's the amount that's put into the account to start, right? And R is the yearly interest rate. And then, of course, T is time in years. And then N is the number of compounds every year. We'll say the number of yearly compounds. All right, so using this equation then, let me scooch this up so we don't lose it. Let's look at this question. Suppose that $100,000 is invested at 6.5% interest compounded semi-annually. So semi-annually means 2 compounds per year. So in this equation, I have A is what we're trying to solve, but P, I'm just going to write it here. P is 100,000. R is given by this 6.5. So R as a decimal is 0.065. So you need to convert percents into a pure decimal. And then N is 2. And then the question is not here, but let's say then we want to know, find the amount after 8 years. So I would plug everything that I have into this formula. So this becomes then the amount after 8 years is equal to the principal, so 100,000, multiplied by 1 plus R, which is 0.065, divided by 2, all raised to the T, so 8 years, and that's my my number, my formula, my equation. So I would pull out a calculator, and I'm not going to take the time to try to share it because I'll lose one screen in order to get this here. But 0.065 divided by 2 is 0.0325. So I think I'm missing a 0 here because it's 100,000, right? Yep. So it's 100,000 multiplied by 1 point, because 1 plus that, it gives me 1.0325 to the 8th power, right? Now this 1.0325 to the 8th power is awful if you try to, work it out. Oh, my calculator doesn't have powers. Oh, yes, it does. To the 8th. So I get this number here. Let me just grab this. That's the number I get. I don't know why this thing needs to resize my screen every time I print something on it. Like this. So it's, I'm going to write it just like this. It's 100,000 multiplied by that number, right? Now, clearly, I don't need this level of accuracy, because if I actually do this multiplication out, right? This ends up being 129,157. Right, 129,157, 75. 352, and so on and so on, yada, yada, yada. The bank's going to cut you off at the pennies, right? But your calculator will typically hold 8 digits if it's an older, one. Or the newer ones will hold, I just did this on my computer's calculator. It'll hold, literally thousands of digits. You don't really need it, though. So if you put 1.0325, raise it to the 8, and then just multiply that and by 100,000, and then just round this thing to the nearest penny. So rounded to the nearest penny, after 8 years in this account, we have 129,157, and that would be 75 cents. They would round this down, and that's what we'd have in the account. All right. I'm going to clear this out. My whiteboard is moving very slow. And now it's frozen. There we go. All right. This should be better. E. So you're probably familiar at this point in your lives with pi, which is some number 3.1415926, blah, 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 goes on forever. E is another such number named for Euler, who was a famous mathematician. But if I compound over and over and over, right? If I go to the bank and I say I want to drop this money into the account, and they say, great, we'll compound it every year, that means I get one compound. And compounding interest is amazing, because if you compound money and then the next month you compound more, they give you money on the money that they already gave you. So money that they gave to you, now they're paying you more money on, right? And so if I compound monthly, it's far better for me than compounding once a year. If I compound daily, it's even better. And somebody thought, well, geez, how far can I push this? Right? And I mean, people did this before Euler, but Euler wrote in depth about it. And he said, all right, well, I'm going to try. What if we compound daily? What if we compound hourly? What if I compound every minute? What if I compound every second? What if I compound, so-and-so, 10 million times every second? At what point does this become more work than it's worth? And so he worked this out. Just the if principal were $1, just the middle part of that function. And so if you started with $1, right, you compounded annually, you'd end up with $2, right? And then if you compounded semi-annually, you'd end up with $2.25. If you did it 3 times, you'd get $2.37, and such and such. And so then he just kept going. If you compound 5 times, if you compound 100 times, if you compound it every day, and you can see the gains on the right-hand side start to become less and less. And so he said, well, what if we kept pushing it? What if we just push it and push it and push it and push it? And there's a limit to how far you can push it before it's no longer valuable. But if you, and limits are a huge thing in math, so we're not going to go into the huge depth with them. But if I kept pushing for more and more compounds, I won't ever get above this number here, right? And that number is Euler's number, right? So this is what happens when things are continuously compounded. compounding infinitely many times. Right. Then you're not going to get better than that number. But if you compound infinitely, that is the number that you end up getting, and it ends up to be the number. It's everywhere in nature. It's in biological models. It's in financial models. It's everywhere. And so let's throw an application here real quick. I won't do it because I know we've got like 5 minutes left. It'll take me longer to go through it, but let's just steal this example from the book. They've got two here, but we'll just look at one. All right. So, and in your calculators, a lot of these calculators are very powerful. You can just graph this stuff in your calculator. But we're going to graph f of x equals e to the x. And so that number, that 2.718 blah, 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 you can, if you're doing this by hand, you can estimate it with 2.718 as your e. But if I plug in these values, right, e in my calculator, and we're not looking at this guy right here, but in my calculator, if I type in that e to the x key and my x is -2, then e to the -2, and try this on your calculator because now's the time to learn this, and the test is the terrible time to learn this. But e to the -2 should give you that 0.135. E to the -1 should give you 0.368. And if we took the time to go through this and graph it, we would end up with this graph here. And that's 5.2. Give your homework a go. In the meantime, do you have any questions for me now?
Hi.
Hi.
I was just wondering, I'll be out of town all week next week. When would you want me to give you my exam?
So take pictures of it, and if you can use a program like Cam Scanner to make a PDF of it and email it to me on Monday, that would be great.
Okay, perfect. Thank you so much.
You're welcome. Any others? Okay. Then I will see you guys Monday. Have a great rest of your weekend.